But what happens if there's more than one charge? We can still draw the electric field by mapping the way a positive test charge would move. In this case, we have a positive and a negative charge close to each other. You can see that the field is actually the sum of the fields due to each point, so that the lines are pointing away from the positive charge and move towards the negative. There are 3 sample points there, labelled 1, 2 and 3. They have arrows on them showing the exact direction of the field at those points. So if you released a positive charge from any of those, the arrow shows the direction that it would move. So far we've only shown fields as if they were 2-dimensional because we're drawing them on flat surfaces. But don't forget that many fields you encounter in real life are 3-dimensional, and it's always worth pointing that out to students as well. Later in this course, we'll be showing you how to put 3 dimensions of fields into diagrams. So there are rules that electric fields always follow and that you need to remember. You've seen a few of them already, but now we're going to put them all together in one group. So first rule is they come out of a positive charge and go into a negative charge. So we always have to put arrows on field lines, and the arrows go from positive to negative. Rule 2 is the closeness of the field lines shows the strength of the electric field in that area. In the picture you can see that these 2 charges aren't equal. So if you were to count the lines at each surface, you would see that the plus 2Q charge has 16 lines coming out from it, and the minus Q charge has only 8 lines going in. The area around the 2Q charge that has the closest field lines is showing the area of the strongest field. Rule 3 is they always enter or leave a conducting surface at right angles. You can see that they've come out horizontally from the vertical plates at the side, but for the circle in the middle, the field lines have actually curved around so that they reach the surface at right angles. Rule 4 is that field lines can never cross, so they have to curve away from each other at top and bottom for the field between these 2 positive charges. If you think about it, a test charge would move away from each positive charge, but right in the middle, midway between them, there's a point where a test charge would be equally repelled by each positive, and so the net force would be 0. This means the electric field at that point must also be 0. You can see it from the big gap in the lines, remembering that the further apart the lines are, the weaker the field. Rule 4 is really just a natural extension of the vector addition of forces, and therefore vector addition of fields. You can see that the positive charge on the right is feeling a force because of each of charges A and B, and so the net force on it will be the sum of those 2, and so that will be the direction of the net electric field at that point. Rule 5 is that once you've got your field, positive charges travel in the direction of the field lines and negative charges go in the opposite direction. Another thing worth remembering is that they can move. Because charges can move in space, that means the fields around them can move as well. One thing for you to do now, explain how can you tell from those field lines that both white charges are the same sign and that black and white must be opposites.